Now we'll look at some very simple electric components to look at a resistor, an inductor, and a capacitor to see the relationship between the voltage and the current going through these simple elements. First, we'll look at a resistor. So let's say we have a resistor here. And in this case, we'll have a resistance of 10 ohms. And we'll have a current going through of 3 amps. So what I'm going to be interested in here is I want to know what's the voltage drop across this resistor as I go from one end to the other, the left side to the right side. The current enters and travels left to right here. Well, we know for that a resistor, it's going to follow Ohm's law. At least the relationship between the voltage and the current is going to follow Ohm's law. V equals IR is what we want to apply here. In this case, we do not know the voltage, but we're told that 3 amps of current passes through it. So I'll keep the units with it. So 3 amps times 10 ohms of resistance here is going to give us 3 times 10 is 30. And amps times ohms, everything in base units, is going to be in volts. So the voltage drop across this resistor is going to be 30 volts. So that was a resistor, just simply Ohm's law, V equals IR. All right, let's look at an inductor next. So there's our inductor, and let's say that the inductance is 4 millihenry. And the current going through it is going to not be constant this time. The current is going to be 5t plus 5, and that's in amps. So once again here, let's look at what the voltage drop is as we go from the left side to the right side of this inductor. So from the notes, the voltage dropping across an inductor is going to be its inductance times the time derivative of the current. So di dt. Voltage we don't know, that's what we're looking for here. Our inductance is 4 millihenry. I'm going to put this into base units. So 4 times 10 to the negative 3 Henry. And then di dt, we're already in base units here in amps. I need to take the time derivative, so 5t plus 5 is just going to be 5, and that's amps per second when I take the time derivative. Right, so I have henries times amps per second. So let's first resolve the numerical part. The 4 times 10 to the negative third times 5 is going to give us 20 times 10 to the negative 3. And we'll have henries times amps per second. But that is also going to be a volt. So we can write it as 20 times 10 to the negative 3 volts, which is the same as 20 millivolts across it. So either of these would be an acceptable way to write it, either in the base units of volts or converting it into the millivolts. And finally, let's look at a capacitor here. Build a very simple circuit where I'll have some voltage source, and then that will go through a capacitor. So our capacitor is this symbol here, these two lines of the same length, whereas above where we have a short line and a long line, that is going to be a voltage source. We'll have a non-constant voltage source of 3 times t volts. So the voltage will increase linearly in time. And we're going to have a capacitor here with a capacitance of 0.4 farad. And what we're interested in is what is the current going through this loop of our very simple circuit. Now, in the capacitor, we have a relationship here that the current going across the capacitor is the capacitance times the time derivative of the voltage. So current equals capacitance times dV dt. And the current, again, is what we're looking at. I'm writing it here as capital I so that we don't confuse it with the square root of -1, which is little I. But we'll be more careful when we get to the electronics component of the course that capital letters are going to be in the frequency domain. Lowercase letters generally then are going to be in the time domain. So it's a little bit mixed in this one, but I want to know what I is. So 0.4 farad, I'm already in base units, so I'll keep it that way, times dV dt. So the time derivative of the voltage is just going to be 3 volts per second when I take the time derivative. All right, so working this out, 0.4 times 3 is going to give me 1.2 farad volts per second. I will be able to rewrite that as amps, which is my unit of current. So the current going through my capacitor here is a constant 1.2 amps. And in these examples, the voltage in the previous one and in the first one were constant. But in general, that doesn't have to be true. The voltage across these elements or the current across these elements can be changing in time, and we will be seeing that. But we want to look at these basic relationships between the voltage across the element and the current across the element and how they're going to be different for these three basic electronic components we're going to be working with: the resistor, the inductor, and the capacitor.